So we're going to talk today about binary search trees, something called randomly built binary search trees. And I'll abbreviate binary search trees as BSTs throughout the lecture. And you've all seen binary search trees in one place or another, in particular a recitation on Friday. So we're going to build off of the basic ideas presented there and talk about how to randomize them and make them good. So you know that there are good binary search trees, which are relatively balanced, something like this. If the height is log n, we call them balanced, and that's good. Anything order log n will be fine. In terms of searching, will then cost order log n. And there are bad binary search trees, which have really large height, possibly as big as n. So this is good, and this is bad. We'd sort of like to know, we'd like to build binary search trees in such a way that they're good all the time, or at least most of the time. And there are lots of ways to do this, and in the next couple of weeks we'll see 4 of them, if you count the problem set, I believe. Today, we're going to use randomization to make them balanced most of the time, in a certain sense. And then in your problem set, you'll make that in a broader sense. But the one way to motivate this topic, so I'm not going to define randomly built binary search trees for a little bit. One way to motivate the topic is through sorting, our good friend. So there's a natural way to sort n numbers using binary search trees. So if I give you an array A, how would you sort that array? Using binary search tree operations as a black box. Yeah?
Build the binary search tree and then traverse it in order.
Build the binary search tree and then traverse it in order, exactly. So let's say we have some initial tree, which is empty, and then for each element of the array, we insert it into the tree. That's what you meant by building the search tree. So we insert AI into the tree. This is the binary search tree insertion, standard insertion. And then we do an in-order traversal, which in the book is called in-order tree walk. Okay, you should know what these algorithms are, but just for a very quick reminder, tree insert walk basically searches for that element AI until it finds the place where it should have been if it was in the tree already, and then adds a new leaf there to insert that value. Tree walk recursively walks the left subtree, then prints out the root, and then recursively walks the right subtree. And by the binary search tree property, that will print the elements out in sorted order. So let's do a quick example, because this turns out to be related to another sorting algorithm we've seen already. So while the example is probably pretty trivial, the connection is pretty surprising. At least it was to me the first time I taught this class. So my array is 3, 1, 8, 2, 6, 7, 5. And I'm going to visit these elements in order from left to right and just build a tree. So the first element I see is 3. So I insert 3 into an empty tree. That requires no comparisons. Then I insert 1. I see is 1 bigger or less than 3? It's smaller, so I put it over here. Then I insert 8. That's bigger than 3, so it gets a new leaf over here. Then I insert 2. That fits between 1 and 3, and so it would fall off this right child of 1. So I add 2 there. 6 is bigger than 3, less than 8, so it goes here. 7 is bigger than 3, less than 8, bigger than 6, so it goes here. And 5 fits in between 3 and 5. 3 and 6, rather. And so that's the binary search tree that I get. Then I run an in-order traversal, which will print 1, 2, 3, 5, 6, 7, 8. Okay, I can run that quickly in my head because I've got a big stack, but be a little bit careful. Of course, you should check that they come out in sorted order. 1, 2, 3, 5, 6, 7, 8. And if you don't have a big stack, you can go and buy one. Always useful. Memory costs are going up a bit these days, or going down. They should be because of the politics. But price fixing, whatever. So the question is, what's the running time of this algorithm? And there's no, I mean, here, this is one of those answers where it depends. The parts that's easy to analyze are, well, initialization. The in-order tree walk, how long does that take? N, good. So there's order n for the walk and for the initialization, which is constant. The question is, how long does it take me to do n tree inserts? Anyone want to guess any kind of answer to that question? Other than it depends. I've already stolen the thunder there. Yeah.
Big omega of n log n.
Big omega of n log n, that's good. It's at least n log n. Why?
Well, because of the decision tree rule, but also because each one is perfectly balanced is going to take roughly log n to find the spot, and you're going to have n of x do, but it could be worse than that.
Right. So you gave two reasons. The first one is because of the decision tree lower bound. That doesn't actually prove this. You have to be a little bit careful. This is a claim that it's omega n log n in all the time. It's certainly omega n log n in the worst case. Every comparison-based sorting algorithm is omega n log n in the worst case. It's also n log n every single time, omega n log n, because of the second reason you gave, which is the best thing that could happen is we have a perfectly balanced tree. So this is the figure that I have drawn the most on a blackboard in my life. The perfect tree on 15 nodes, I guess. So if we're lucky, we have this, and if you add up all the depths of the nodes here, which gives you the search tree cost, in particular, these n over 2 nodes in the bottom each have depth log n, and therefore you're going to have to pay at least n log n for those. And if you're less balanced, it's going to be even worse. That takes some proving, but it's true. So it's actually omega n log n all the time. Okay, you've seen that there are some cases, like if you know that the elements are almost already in order, you can do it in a linear number of comparisons. So, but here you can't. Any other guesses at an answer to this question? Yeah.
Big O n squared.
Big O n squared. Good. Why?
Because you're doing n things, and each of them are big O of n because, that's how many are in the tree. So.
Right. We're doing n things, and each node has depth at most n. So the number of comparisons we're making per element we insert is at most n. So that's at most n squared. Any other answers? Is it possible for this algorithm to take n squared time? Are there instances where it takes theta n squared?
It's already sorted.
If it's already sorted, that would be pretty bad. So if it's already sorted, or if it's reverse sorted, you're in bad shape, because then you get a tree like this. This is the sorted case. And you compute, so the total cost, the time in general is going to be the sum of the depths of the nodes for each node x in the tree. And in this case, it's 1 plus 2 plus 3 plus 4, this arithmetic series. There's n of them, so this is theta n squared. It's like n squared over 2. So that's bad news. The worst case running time of this algorithm is n squared. Does that sound familiar at all? An algorithm's worst case running time is n squared, in particular in the already sorted case? But if we're lucky, right, the lucky case would be if the, as we said, it's a balanced tree. Wouldn't that be great? Anything with omega log n height would give us a sorting algorithm that runs in n log n. So in the lucky case, we're n log n, but in the unlucky case, we're n squared. And unlucky is sorted. Remind you of any algorithm we've seen before? Yeah? Quicksort. Turns out the running time of this algorithm is the same as the running time of quicksort in a very strong sense. Turns out the comparisons that this algorithm makes are exactly the same comparisons that quicksort makes. It makes them in a different order, but it's really the same algorithm in disguise. That's the surprise here. So in particular, we've already analyzed quicksort. We should get something for free out of that analysis. So the relation is BST sort and quicksort make the same comparisons. But in a different order. So let me walk through the same example we did before. 3, 1, 8, 2, 6, 7, 5. So there's an array. We're going to run a particular version of quicksort. I have to be a little bit careful here. Sort of the obvious version of quicksort. Remember, our standard boring quicksort is you take the first element as the partition element. So I'll take 3 here. And I split into the elements less than 3, which is 1 and 2, and the elements bigger than 3, which is 8, 6, 7, 5. And in this version of quicksort, I don't change the order of the elements 8, 6, 7, 5. So let's say the order is preserved, because only then will this equivalence hold. So this is sort of a stable partition algorithm. It's easy enough to do. It's a particular version of quicksort, and soon we're going to randomize, and after we randomize, this difference doesn't matter. Okay, then on the left recursion, we split in the partition element. There's things less than 1, which is nothing, things bigger than 1, which is 2, and then that's our partition element, we're done. Over here, we partition on 8. Everything is less than 8, so we get 6, 7, 5, nothing on the right. Then we partition at 6. We get things less than 6, namely 5, things bigger than 6, namely 7. And those are sort of partition elements in a trivial way. Now, this tree that we get on the partition elements looks an awful lot like this tree. Okay, it should be exactly the same tree. And you can walk through what comparisons does quicksort make. Well, first, it compares everything to 3. Okay, except 3 itself. Now, if you look over here, what happens when we're inserting elements? Well, each time we insert an element, the first thing we do is compare with 3. If it's less than, we go to the left branch. If it's greater than, we go to the right branch. So we're making all these comparisons with 3 in both cases. Then if we have an element less than 3, it's either 1 or 2. If it's 1, we're done. No comparisons happen here, 1 to 1. But we compare 2 to 1. And indeed, when we insert 2 over there, after comparing it to 3, we compare it to 1, and then we figure out that it happens here. Same thing happens in quicksort. For elements greater than 3, we compare every one to 8. Because we're partitioning with respect to 8. here, because that's the next node after 3, as soon as 8 is inserted, we compare everything with 8 to see, in fact, that it's less than 8, and so on. So all the same comparisons, just in a different order, sort of turn 90 degrees. Kind of cool. So this has various consequences in the analysis. So in particular, the worst case running time is theta n squared, which is not so exciting. What we really care about is the randomized version, because that's what performs well. So randomized BST sort is just like randomized quicksort. So first thing you do is randomly permute the array uniformly, picking all permutations with equal probability. And then we call BST sort. Okay, this is basically what randomized quicksort could be formulated as. And then randomized BST sort is going to make exactly the same comparisons as randomized quicksort. Here, we're picking the root essentially randomly. And over here in quicksort, you're picking the partition element randomly. Same difference. Okay, so the time of this algorithm equals the time of randomized quicksort. Because we're making the same comparisons, so the number of comparisons is equal. And this is true as random variables. The random variable, the running time of this algorithm, is equal to the random variable of this algorithm. In particular, the expectations are the same. Okay, and we know that the expected running time of randomized quicksort on n elements is oh boy, n log n. Good. I was a little worried there. Okay, so in particular, the expected running time of BST sort is n log n. Obviously, this is not too exciting from a sorting point of view. And the sorting was just sort of to see this connection. What we actually care about, and the reason I've introduced this BST sort, is what the tree looks like. What we really want is that search tree. The search tree can do more than sort. In-order traversal is a pretty boring thing to do with the search tree. You can search in a search tree. So, okay, that's still not so exciting. You could sort the elements and then put them in an array and do binary search. But the point of binary search trees instead of binary search arrays is that you can update them dynamically. We won't be updating them dynamically in this lecture, but we will in Wednesday and on your problem set. For now, it's just sort of a warm-up. Let's say that the elements aren't changing. We're building one tree from the beginning. We have all n elements ahead of time. We're going to build it randomly. We randomly permute that array. Then we throw all the elements into a binary search tree. That's what BST sort does. Then it calls in-order traversal. I don't really care about in-order traversal. What I want, because we've just analyzed it. It would be a short lecture if I were done. What we want is this randomly built BST, which is what we get out of this algorithm. So this is the tree resulting from random BST sort, randomized BST sort. Okay, resulting from randomly permuting the array and just inserting those elements using the simple tree insert algorithm. Question is, what does that tree look like? And in particular, is there anything that we can conclude out of this fact, that the expected running time of BST sort is n log n? Okay, I've mentioned cursorily what the running time of BST sort is several times. It was the sum, so this is the time of BST sort. on n elements. It's the sum over all nodes x of the depth of that node. Okay, depth starts at 0 and works its way down. Because the root element, you don't make any comparisons. Beyond that, you're making whatever the depth is comparisons. Okay, so we know that this thing is, in expectation, we know that this is n log n. What does that tell us about the tree? This is for all nodes x in the tree. Does it tell us anything about the height of the tree, for example? Yeah?
I mean, in some intuitive sense, it says that the height's about log n, theta log n and not theta n.
Right. Intuitively, it says the height of the tree is theta log n and not n. But in fact, it doesn't show that. And that's why you feel that that's just intuition, but it may not be quite right. Indeed, it's not. Let me tell you what it does say. So if we take expectation of both sides, here we get n log n. So the expected value of that is n log n. So over here, well, we get the expected total depth, which is not so exciting. Let's look at the expected average depth. So if I look at 1 over n, the sum over all n nodes in the tree of the depth of x, that would be the average depth over all the nodes. And what I should get is theta n log n over n, because I divided n on both sides. And I'm using here linearity of expectation, which is log n. So what this fact about the expected running time tells me is that the average depth in the tree is log n, which is not quite the height of the tree being log n. Okay, remember the height of the tree is the maximum depth of any node. Here we're just bounding the average depth. So let's look at an example of a tree. Draw my favorite picture. So here we have a nice balanced tree, let's say on half of the nodes or a little more. And then I have one really long path hanging off one particular leaf, doesn't matter which one. And I'm going to say that this path has length, well, the total height here I want to make root n, which is a lot bigger than log n. This is roughly log n. It's going to be log of n minus root n or so, roughly. So most of the nodes have logarithmic height. And if you compute, logarithmic depth, if you compute the average depth in this particular tree, for most of the nodes, let's say it's at most, like half of the, let's say, at most n of the nodes have height log n. And then there are root n nodes at most down here, which have depth at most root n. So let's say it's at most root n times root n. In fact, it's like half that, but not a big deal. So this is n. So this is n log n. Or sorry. Average depth, I have to divide everything by n. N log n would be rather large for an average height. Average depth. So the average depth here is log n, but the height of the tree is square root of n. So this is not enough. Just to know that the average depth is log n doesn't mean that the height is log n. Okay, but the claim is, the theorem for today is that the expected height of a randomly built binary search tree is indeed order n log n, or sorry, log n. BST order log n. This is what we'd like to know, because that tells us if we just build a binary search tree randomly, then we can search in it in log n time. Okay, for sorting, it's not as big a deal. We just care about the expected running time of creating the thing. Here, now we know that we can, once we prove this theorem, we know that we can search quickly in expectation, okay, which, in fact, most of the time. So the rest of today's lecture will be proving this theorem. It's quite tricky, as you might imagine. It's another big probability analysis along the lines of quicksort and everything. Yeah. So I'm going to start with an outline of the proof. Unless there are any questions about the theorem, it should be pretty clear what we want to prove. This is even weirder than most of the analyses we've seen. It's going to use a fancy trick, which is exponentiating a random variable. And to do that, we need a tool called Jensen's inequality. We're going to prove that tool. Usually we don't prove probability tools, but this one we're going to prove. It's not too hard. It involves some basic analysis. So the theorem, or the lemma, says that if we have what's called a convex function f, and you should all know what that means, but I'll define it soon, in case you've forgotten. If we have a convex function f and we have a random variable x, you take f of the expectation, that's at most the expectation of f of that random variable. Okay? Think about it enough and draw convex functions. That is fairly intuitive, I guess. But we'll prove it. What that allows us to do is, instead of analyzing the random variable that tells us the height of a tree, so xn, I'll call the random variable rv of the height of a BST, randomly constructed BST on n nodes. We'll analyze, well, instead of analyzing this desired random variable xn, sorry, this should have been a capital X. We're going to analyze, we can analyze any convex function of xn, and we're going to analyze the exponentiation. So I'm going to define yn to be 2 to the power xn. Okay. The big question here is, why bother doing this? The answer is because it works, and it wouldn't work if we analyze xn. We'll see some intuition of that later on, but it's not very intuitive. This is just a bizarre analysis where you need this extra trick. So we're going to bound the expectation of yn, and from that, and using Jensen's inequality, we're going to get a bound on the expectation of xn, a pretty tight bound, actually. Because if we can bound the exponent up to constant factors, the exponentiation up to constant factors, we can bound xn even better, because you take logs to get xn. So we'll even figure out what the constant is. So what we'll prove, this is the heart of the proof, is that the expected value of yn is order n cubed. Here we won't really know what the constant is. Don't need to. And then we put these pieces together. So let's do that. What we really care about is the expectation of xn, which is the height of our tree. What we find out about is this fact. So leave some horizontal space here. We get the expectation of 2 to the xn. That's the expectation of yn. So we learn that that's order n cubed. And Jensen's inequality tells us if we take this function 2 to the x, we plug it in here, then on the left-hand side, we get 2 to the e of x. So we get 2 to the e of xn is at most e of 2 to the xn. So that's where we use Jensen's inequality, because what we care about is e of xn. So now we have a bound. We say, well, 2 to the e of xn is at most n cubed. So if we take the log of both sides, we get e of xn is at most the log of n cubed. Okay, I'll write it in this funny way, log of order n cubed, which will actually tell us the constant. This is 3 log n plus order 1. So we will prove that the expected height of a randomly constructed binary search tree on n nodes is roughly 3 log n at most. Okay, I'll say more about that later. So you've now seen the end of the proof. That's the foreshadowing. And now this is the top-down approach. So you sort of see what the steps are. Now we just have to do the steps. Okay, step 1 will take a bit of work, but it's easy because it's pretty basic stuff. Step 2 is just a definition. We're done. Step 3 is probably the hardest part. And step 4 we've already done. So let's start with step 1. So the first thing I need to do is define a convex function, because we're going to manipulate that definition a fair amount. So this is a notion from real analysis. Analysis is a fancy word for calculus. If you haven't taken the proper analysis class, you should have seen convexity in any calculus class. A convex function is one that looks like this. Okay, good. One way to formalize that notion is to consider any 2 points on this curve. So I'm only interested in functions from reals to reals. So it looks like this. This is f of something, and this is the something. If I take 2 points on this curve, and I draw a line segment connecting them, that line segment is always above the curve. That's the meaning of convexity. It has a geometric notion which is basically the same. But for functions, this line segment should stay above the curve. The line does not stay above the curve. If I extended it farther, it goes beneath the curve, of course. But that segment should. So I'm going to formalize that a little bit. I'll call this x, and then this is f of x. And I'll call this y, and this is f of y. So the claim is if I take any number between x and y, and I look up, and I say, OK, here's the point on the curve. Here's the point on the line segment. The value of that point on the y value here should be greater than or equal to the y value here. Okay? To figure out what this point is, we need some, I would call it geometry. I'm sure it's an analysis concept too, but I'm a geometer, so I get to call it geometry. If you have 2 points, P and Q, and you want to parameterize this line segment between them, so I want to parameterize some point here, the way to do it is to take a linear combination. And if you should have taken some linear algebra, linear combination looks something like this. And in fact, we're going to take something called an affine combination, where alpha plus beta equals 1. Okay? It turns out if you take all such points, some number alpha times the point P plus some number beta times the point Q, where alpha plus beta equals 1. If you take all those points, you get the entire line here, which is nifty, but we don't want the entire line. If you also constrain alpha and beta to be non-negative, you just get this line segment. So this forces alpha and beta to be between 0 and 1, because they have to sum to 1 and they're non-negative. So what we're going to do here is take alpha times x plus beta times y. That's going to be our point in between. With these constraints, alpha plus beta equals 1, alpha and beta are greater than or equal to 0. Then this point is f of that. This is f of alpha x plus beta y. And this point is the linear interpolation between f of x and f of y, the same one. So it's alpha times f of x plus beta times f of y. Okay, that's the intuition. If you didn't follow it, it's not too big a deal because all we care about are the symbolic answer for proving things. But that's where this comes from. So here's the definition. Its function is convex if for all x and y and all alpha and beta greater than or equal to 0, whose sum is 1, we have f of alpha x plus beta y is less than or equal to alpha f of x plus beta f of y. So that's just saying that this y coordinate here is greater than this y, or is less than or equal to this y coordinate. Okay, but that's the symbolism behind that picture. Okay, so now we want to prove Jensen's inequality. Okay, we're not quite there yet. We're going to prove a simple lemma from which it will be easy to derive Jensen's inequality. So this is the theorem we're proving. So here's a lemma about convex functions. You may have seen it before. It will be crucial to Jensen's inequality. Yeah, okay. We have. So suppose this is a statement about affine combinations of n things instead of 2 things. So this will say that convexity can be generalized to taking n things. So suppose we have n real numbers, and we have n values alpha I, alpha 1 up to alpha n. They're all non-negative, and their sum is 1. So the sum of alpha k, I guess, k equals 1 to n, is 1. So those are the assumptions. The conclusion is the same thing but summing over all k. So k equals 1 to n, alpha k xk. Take f of that versus taking the sum of the alphas times the f's. K equals 1 to n. So the definition of convexity is exactly that statement, but where n equals 2. Okay, alpha 1 and alpha 2 are alpha and beta. This is just a statement for general n. And you can interpret this in some funnier way, which I won't get into. Oh, sure, why not? I'm a geometer. So this is saying you take several points on this curve. You take the polygon that they define. So these are straight line segments. You take the interior. If you take an affine combination like that, you will get a point inside that polygon, or possibly on the boundary. The claim is that all those points are above the curve. Again, intuitively true from if you draw a nice canonical convex curve, but in fact it's true algebraically too. Always a good thing. Any suggestions on how we might prove this theorem, this lemma? It's pretty easy. So what technique might we use to prove it? One word. Induction, always a good answer. Yeah. Induction should shout out at you here because we already know that this is true by definition of convexity for n equals 2. So base case is clear. In fact, there's an even simpler base case, which is when n equals 1. If n equals 1, then you have one number that sums to 1, so alpha 1 is 1. And so nothing's going on here. This is just saying that f of 1 times x1 is at most 1 times f of x1. So not terribly exciting, because that holds with equality. Okay, so we don't even need the n equals 2 base case. So the interesting part, although still not terribly interesting, is the induction step. This is good practice in induction. So what we care about is this f of the sum, this linear combination, f of this linear combination, affine combination, xk times xk summed over all k. Now, what I would like to do is apply induction. What I know about inductively is say f of this sum if it's summed only up to n minus 1 instead of all the way up to n. Any smaller sum I can deal with by induction. So I'm going to try and get rid of the nth term. I want to separate it out. And this is fairly natural if you've played with affine combinations before, but it's just some algebra. So I want to separate out the alpha n x n term. And I'd also like to make it an affine combination. This is the trick. Sorry, no f here. If I just removed the last term, the alpha k's from 1 up to n minus 1 wouldn't sum to 1 anymore. They'd sum to something smaller. So I can't just take out this term. I'm going to have to do some trickery here. xk, close the f. Good. So you should see why this is true, because the 1 minus alpha n's cancel, and then I'm just getting the sum of alpha k xk, k equals 1 to n minus 1, plus the alpha n xn term. So I haven't done anything here. These are equal. But now I have this nifty feature that on the one hand, these two numbers, alpha n and 1 minus alpha n, sum to 1. And on the other hand, if I did it right, these numbers should sum up to 1. Just going from 1 up to n minus 1. Why do they sum up to 1? Well, these numbers summed up to 1 minus alpha n. And so I'm dividing everything by 1 minus alpha n, so they will sum to 1. So now I have two affine combinations. I just apply the two things that I know. I know this affine combination will work because, well, why? Why can I say that this is alpha n f of xn plus 1 minus alpha n f of this crazy sum? Shout it out. There are two possible answers. One is correct and one is incorrect. So which will it be? Oops, this should have been less than or equal to. It's important. It's on the board. Can't be too difficult. So I'm treating this as just one big x value. So I have some xn and I have some crazy x. I want f of the affine combination of those two x values is at most the affine combinations of the f's of those x values. This is?
The inductive hypothesis with n equals 2.
It is the inductive hypothesis with n equals 2. Unfortunately, we didn't prove the n equals 2 case is a special base case. So we can't use induction here, the way that I've stated the base case. If you did n equals 2 base case, you could do that. Here we can't. So the other answer is? By convexity. Good. That's right here. Okay, so f is convex. We know that this is true for any two values of x for any two x values, and provided these two sum to 1. So we know that this is true. Now is when we apply induction. So we know, so now we're going to manipulate this right term by induction. See, before we didn't necessarily know that n was bigger than 2. But we know that n is bigger than n minus 1. That much I can be sure of. So this is 1 minus alpha n times the sum, k equals 1 to n minus 1, of alpha k over 1 minus alpha n times f of xk. If I got that right. This is by induction, the induction hypothesis. Because these alpha k's over 1 minus alpha n sum to 1, now these 1 minus alpha n's cancel, and we just get what we want. This is sum k equals 1 to n of alpha k f of xk. So we get that f of the sum is at most sum of the f's. That proves the lemma. Okay, a bit tedious, but each step is pretty straightforward. Hope you agree. Now it turns out to be relatively straightforward to prove Jensen's inequality. That's the magic. And then we get to do the expectation analysis, which we'll use our good friends, indicator random variables. Okay, but for now, we just want to prove this statement. If we have a convex function, f of the expectation is at most expectation of f of that random variable. Okay, this means this is a random variable, right? If you want to sample from this random variable, you sample from x, then you apply f to it. That's the meaning of this notation f of x, because x is a random variable. We get to use that f is convex. Okay, it turns out this is not hard. If you remember the definition of expectation. Oh, I want to make one more assumption here, which is that x is integral. So it's an integer random variable, meaning it takes integer values. Okay, that's all we care about because we're looking at running times. This statement is true for continuous random variables too, but I would like to do the discrete case, because then I can write down what e of x is. So, what is the definition of e of x? X only takes on integer values. This is easy, but you have to remember it. Good drill. I don't really know much about x except that it takes on integer values. Any suggestions on how I should expand the expectation of x? How many people know this by heart? Okay, it's not too easy then. Well, expectation has something to do with probability, right? So I should be looking at something like the probability that x equals some value x. That would seem like a good thing to do. What else goes here? A sum, yeah. Sum, well, x could be somewhere between minus infinity and infinity. That's certainly true. And you have some more? Something missing here. What is this sum? What does it come out to? For any random variable x that takes on integer values. 1. Good. So I need to add in something here, namely x. Okay, that's the definition of the expectation. Now, f of a sum of things where these coefficients sum to 1 looks an awful lot like the lemma that we just proved. Okay, we proved it in the finite case. It turns out it holds just as well if you take all integers. I'm just going to assume that. So I have these probabilities, these alpha values, sum to 1. Therefore, I can use this inequality that this is at most, get this right. I have the alphas, so I have a sum, x equals minus infinity to infinity, of the alphas, which are probability capital X equals little x, times f of the value, f of little x. Okay, so there it is. I've used the lemma, so maybe now I'll erase the lemma. Okay, I cheated by using the countable version of the lemma while only proving the finite case, but that's all I can do in lecture. So this is by lemma. Now what I'd like to prove, and leave some blank space here, is that this is at most e of f of x. So that this summation is at most e of f of x. Actually, it's equal to e of f of x. And it really looks kind of equal, right? We've got sum of some probabilities times f of x. It almost looks like the definition of e of f of x, but it isn't. Got to be a little bit careful. Because e of f of x should talk about the probability that f of x equals a particular value. We can relate these as follows. Not too hard. You can look at each value that f takes on. And then look at all the values k that map to that value. X, so all the k's where f of k equals x, the probability that x equals k. Okay, this is another way of writing the probability that f of x equals x. Okay, so in other words, I'm grouping the terms in a particular way. I'm saying, well, f of x takes on various values. Clever of me to switch. I used to use k's in the notes, so I better call this something else. Let's call this y. Sorry. Switch notation here. Makes sense. Probability. I should look at the probability that x equals x. So what I really care about is what this f of x value takes on. Let's just call it y. Look at all the values y that f could take on. That's the range of f. And then I'll look at all the different values of x where f of x equals y. If I add up those probabilities, because these are different values of x, those are sort of independent events. So this summation will be the probability that f of x equals y. This is capital X. This is little y. And then if I multiply that by y, I'm getting the expectation of f of x. So think about this. These two inequalities hold. It's maybe a bit bizarre here because these sums are potentially infinite. But it's true. Okay, this proves Jensen's inequality. So it wasn't very hard, just a couple of boards. Once we had this powerful convexity lemma. So we just use convexity. We use the definition of e of x. We use convexity. That lets us put the f's inside. Then we do this regrouping of terms, and we figure out, oh, that's just e of f of x. So the only inequality here is coming from convexity. All right. Now comes the algorithms. So this was just some basic probability stuff, which is good to practice. Okay, we could see in the quiz, which is not surprising, this is the case for me too, you have a lot of intuition for algorithms. Whenever it's algorithmic, it makes a lot of sense because you're sort of grounded in something that you know because you're computer scientists or something of that ilk. For the purposes of this class, you're computer scientists. But with sort of the basic probability, unless you happen to be a mathematician, it's less intuitive and therefore harder to get fast. And in quiz 1, speed is pretty important. On the final, speed will also be important. The take-home certainly doesn't hurt. So the take-home is more interesting because it requires being clever. You have to actually be creative. And that really tests algorithmic design. So far, we've mainly tested analysis and just can you work through probability? Can you figure out can you remember what the running time of randomized quicksort is, and so on. Quiz 2 will actually test creativity because you have more time. It's hard to be creative in 2 hours. Okay, so we want to analyze the expected height of a randomly constructed binary search tree. So as I've defined this before, but let me repeat it because it was a while ago, almost the beginning of lecture. I'm going to take the random variable of the height of a randomly built binary search tree on n nodes. So that was randomize the n values, take a random permutation, insert them one by one from left to right with tree insert. What is the height of the tree that you get? What is the maximum depth of any node? I'm not going to look so much at xn. I'm going to look at the exponentiation of xn. And still we have no intuition why. But 2 to the x is a convex function. Okay, it looks like that. It's very sharp. That's my best I can do for drawing 2 to the x. You saw how I drew my histogram. Okay, so we want to somehow write this random variable as something, okay, in some algebra. And the main thing here is to split into cases. That's how we usually go, because there's lots of different scenarios of what happens. So, I mean, how do we construct a tree from the beginning? First thing we do is we take the first node, we throw it in, make it the root. Okay, so whatever the first value happens to be in the array, which we don't really know how that falls in the sorted order, we put it at the root. And it stays the root. We never change the root from then on. Now, of all the remaining elements, some of them are less than this value, and they go over here. So let's call this r for the root. And some of them are greater than r, so they go over here. Maybe there's more over here, maybe there's more over here. Who knows? Arbitrary partition. In fact, uniformly random partition, which should sound familiar. Whether there are k elements over here and n minus k minus 1 elements over here is, for any value of k, that's equally likely, because this is chosen uniformly. The root is chosen uniformly. It's the first element in a random permutation. So what I'm going to do is parameterize by that. How many elements are over here and how many elements are over here? Because this thing is, again, a randomly built binary search tree on however many nodes are in there. Because after I pick r, it's determined who's to the left and who's to the right. And so I can just partition. It's like running quicksort. I partition the elements left of r, the elements right of r. And I'm sort of recursively constructing a randomly built binary search tree on those two subpermutations, because subpermutations of uniform permutations are uniform. Okay, so these are essentially recursive problems. And we know how to analyze recursive problems. All you need to know is that there are k minus 1 elements over here and n minus k elements over here. And that would mean that r has rank k. Remember, rank in the sense of the index in the sorted order. So where should I go? So if the root R has rank k, so this is a statement about conditioned on this event, which is a random event, then what we have is xn equals 1 plus the max of xk minus 1, xn minus k. Because the height of this tree is the max of the heights of the two subtrees plus 1, because we have one more level up top. Okay, so that's the natural thing to do. What we are trying to analyze, though, is yn. So for yn, we have to take 2 to this power. So it's 2 times the max of 2 to the xk minus 1, which is yk minus 1, and 2 to this, which is yn minus k. And now you start to see maybe why we're interested in y's instead of x's, in the sense that it's what we know how to do. When we solve a recursion, when we solve like the expected running time, we haven't taken expectations yet here, but when we compute the expected running time of quicksort, we have something like 2 times, we have a couple of recursive subproblems which are being added together. Okay, here we have a factor of 2, here we have a max. But intuitively, we know how to multiply random variables by a constant, because that's like there's 2 recursive subproblems of the size equal to the max of these 2, okay, which we don't happen to know here, but there it is. Whereas 1 plus, we don't know how to handle so well. And indeed, our techniques are really good at solving recurrences, except up to the constant factors. And this 1 plus really doesn't affect the constant factor too much, it would seem. Okay, but it's a big deal. In exponentiation, it's a factor of 2. So here, it's really hard to see what this 1 plus is doing. And our analysis, if we tried it, and it's a good idea to try it at home and see what happens, if you try to do what I'm about to do with xn, the 1 plus will sort of get lost, and you won't get a bound. Just can't prove anything. With a factor of 2, we're in good shape. We sort of know how to deal with that. I'll say more when we've actually done the proof about why we use yn instead of xn. But for now, we're using yn. So this is sort of a recursion, except it's conditioned on this event. So how do I turn this into a statement that holds all the time? This should, sorry? Divide by the probability of the event, more or less. Indeed. These events are independent, or they're all equally likely, I should say. They're not independent. In fact, one determines all the others. So how do I generally represent an event in algebra? Indicator random variables. Good. Remember your friends, indicator random variables. All of these analyses use indicator random variables. So they will just represent this event, and we'll call it znk. It's going to be 1 if the root has rank k, and 0 otherwise. So in particular, the probability of these things are all equally likely. For a particular value of n, if you try all the values of k, the probability that this equals 1, which is also the expectation of that indicator random variable, which you should know, because it only takes values 1 or 0. The 0 doesn't matter in the expectation. So this is going to be, hopefully, 1 over n. I got it right. So there are n possibilities of what the rank of the root could be. Each of them is equally likely because we have a uniform permutation. So now I can rewrite this conditional statement as a summation where the z and k's will let me choose what case I'm in. So we have yn is the sum, k equals 1 to n, of z and k times 2 times the max of x, so sorry, y, k minus 1, y, n minus k. So now we have our good friend, the recurrence. We need to solve it. Okay, we can't really solve it because this is a random variable and it's talking about recursive random variables, so we first take the expectation of both sides. That's the only thing we can really bound. Yn could be n squared in an unlucky case. Sorry, not n squared. It could be n squared. It could be 2 to the, could be 2 to the n if you're unlucky, because xn could be as big as n, the height of the tree, and yn is 2 to that. So it could be 2 to the n. What we want to prove is that it's polynomial in n. If it's n to some constant, and we take logs, it'll be order log n. Okay, so we'll take the expectation, and hopefully that will guarantee that this holds. Okay, so we have expectation of this summation of random variables times recursive random variables. So what is the first, I forgot a bracket. What is the first thing that we do in this analysis? This should, yeah, linearity of expectation. That one's easy to remember. Here we have a sum, so let's put the e inside. Okay. Now we have the expectation of a product. What should we use? Independence. Hopefully things are independent. And then we could write this. Then it would be the expectation of the product. And heck, let's put the 2 outside because it's no sense in keeping it in here. Oof. My y's are starting to look like x's. I can't even read them. Sorry about that. It should all be y's. Okay. Very wise random variables. So why are these independent? So here we're looking at the choice of what the root is, what rank the root has in a problem of size n. In here, we're looking at what the root, there are various choices of what the search tree looks like in the stuff left of the root and in the stuff right of the root. Those are independent choices because everything is uniform here. So the choice of this guy was uniform, and then that determines who partitions in the left and the right. Those are completely independent recursive choices of who's the root in the left subtree, who's the root in the left of the left subtree, and so on. So this is a little trickier than usual. Before it was random choices in the algorithm. Now it's in some construction where we choose the random numbers ahead of time. It's a bit funny, but this is still independent. So we get this just like we did in quicksort and so on. Okay. Now we continue. And now it's time to be a bit sloppy. Well, one of these things we know. Okay, e of znk. That we wrote over here. It's 1 over n. So that's cool. So we get a 2 over n outside, and we get this sum of the expectation of a max of these two things. And normally we would write, well, I think that's pretty. Sometimes you write t of max or y of the max of the two things here. We've got to write it as the max of these two variables. And the trick, it's not too much of a trick, is that the max is at most the sum. So we have non-negative things. So we have 2 over n sum k equals 1 to n of the expectation of the sum instead of the max. Okay, this is in some sense the key step where we're losing something in our bound. So far we've been exact. Now we're being pretty sloppy. It's true this max is at most the sum, but it's a pretty loose upper bound as things go. Okay, keep that in mind for later. What else can we do with this summation? This should again look familiar. Now that we have a sum of two things, kind of like it to be a sum of one thing. Sorry? You can use linearity of expectation. Good. So that's the first thing I should do. So linearity of expectation lets me separate that. Now I have a sum of 2n things. Right? I could break that into the sum of these guys and the sum of these guys. You know anything about those two sums? Do we know anything about those two sums? They're the same. In fact, every term here is appearing exactly twice. Once as a k minus 1, once as an n minus k, and that even works if it's odd, I think. So, in fact, we can just take one of the sums and multiply it by 2. So this is 4 over n times the sum, and I'll rewrite it a little bit, from 0 to n minus 1 of e of yk. Just check the number of times that each yk appears from 0 up to n minus 1 is exactly 2. So now I have a recurrence. I have e of yn is at most this thing. Just write that for memory. It's at most that. Cool. Now I just have to solve the recurrence. How should I solve an ugly, hairy recurrence like this? Substitution! Yay! Not the master method. Okay. It's a pretty nasty recurrence. So I'm going to make a guess, and I've already told you the guess, that it's n cubed. I think n cubed is pretty much exactly where this proof will be attainable. So substitution method is just a proof by induction. And there are two things every proof by induction should have. Well, almost every proof by induction, unless you're being fancy. It should have a base case. And the base case here is n equals order 1. I didn't write it, but of course, if you have a constant size tree, it has constant height. So this thing will be true as long as we set true if C is sufficiently large. Okay, so don't forget that. A lot of people forgot it on the quiz. We even mentioned the base case. Usually we don't even mention the base case, and you should assume that there's one there, and you have to say this in any proof by substitution. Okay, now we have the induction step. So I claim that e of yn is at most c of n cubed, assuming that it's true for smaller n. You should write the induction hypothesis here, but I'm going to skip it because I'm running out of time. Now we have this recurrence that e of yn is at most this thing. So e of yn is at most 4 over n sum k equals 0 to n minus 1 of e of yk. Now, notice that k is always smaller than n, so we can apply induction. So this is at most 4 over n sum k equals 0 to n minus 1 of c times k cubed. That's the induction hypothesis. Cool. Now, I need an upper bound on this sum. If you have a good memory, then you know a closed form for this sum. But I don't have such a good memory as I used to. I never memorized this sum when I was a kid, so I don't remember it. You know, everything I memorized when I was less than 12 years old, I still remember. All the digits of pi, whatever. But anything I try to memorize now just doesn't quite stick the same way. So I don't happen to know this sum. What's a good way to approximate this sum? Integral. Good. So in fact, if I'm going to take the c outside also, so this is 4c over n. The sum is at most the integral if you get the range right. So you have to go one larger. Instead of n minus 1, you go up to n. This is in the textbook. It's intuitive, too. As long as you have a monotone function, that's key. So you have something that's like this. And, you know, the sum is taking each of these and weighting them with a value of 1. The integral is computing the area under this curve. So in particular, if you look at this approximation of the integral, then, I mean, this thing is certainly, this would be the sum if you go one larger at the end, and that's at most the integral. So that's proof by picture. But you can see this in the book. You should know it from 042, I guess. Now, integrals, hopefully you can solve. The integral of x cubed is x to the 4th over 4, right? Yeah. Got it right. And then we're valuing that at n, and at 0, subtracting the 0 doesn't matter, because 0 to the 4th power is 0. So it's just n to the 4th over 4. So this is 4c over n times n to the 4th over 4. And conveniently, this 4 cancels with this 4. The 4 turns into a 3 because of this, and we get n cubed. We get c n cubed. Damn convenient, because that's what we wanted to prove. Okay, so this proof is just barely snaking by. No residual term. We've been sloppy all over the place, and yet we were really lucky, and we were just sloppy in the right places. So this is a very tricky proof. If you just try to do it by hand, it's pretty easy to be too sloppy and not get quite the right answer. But this just barely works. So let me say a couple things about it in my remaining 1 minute. So we can do the conclusion again. I won't write it because I don't have time, but here it is. We just proved a bound on yn, which was 2 to the power xn. What we cared about was xn. So we use Jensen's inequality. We get that 2 to the e of xn is at most e of 2 to the xn. This is what we know about, because that's yn. So we know e of yn is now order n cubed. Okay, we had to set this constant sufficiently large for the base case. We didn't really figure out what the constant was here. Didn't matter, because now we're taking the logs of both sides. We get e of xn is at most log of order n cubed. This constant is a multiplicative constant, so you take the logs, it becomes additive. This constant is an exponent, so it take logs, it becomes a multiple. We get 3 log n plus order 1. This is a pretty damn tight bound on the height of a randomly built binary search tree. The expected height, I should say. In fact, the expected height of xn is equal to, well, roughly, I'll just say it's roughly. I don't want to be too precise here. 2.9882 times log n. This is a result by a friend of mine, Luc Devroy. I can spell it right. In 1986, he's a professor at McGill University in Montreal. So we're pretty close, 3 to 2.98, and I won't prove this here. And the hard part here is actually the lower bound, that it's only that much. Right, I should say a little bit more about why we use yn instead of xn. And it's all about the sloppiness. And in particular, this step, where we said that the max of these two random variables is at most the sum. And while that's true for x just as well as it is true for y, it's more true for y. Okay, this is a bit weird. Because remember, what we're analyzing here is all possible values of k. This has to work no matter what k is, in some sense. I mean, we're bounding all of those cases simultaneously, the sum of them all. So here we're looking at k minus 1 versus n minus k. And in fact, here there's a polynomial version. But so if you take two values, a and b, and you say, well, max of ab is at most a plus b. And on the other hand, you say, well, max of 2 to the a and 2 to the b is at most 2 to the a plus 2 to the b. Doesn't this feel better than that? Well, They're, of course, the same. But if you look at a minus b, as that grows, this becomes a tighter bound faster than this becomes a tighter bound. Because here we're looking at absolute value, absolute difference between a minus b. So that's why this is pretty good and this is pretty bad. We're still really bad if a and b are almost the same. But we're trying to solve this for all partitions into k minus 1 and n minus k. So it's okay if we get a few of the cases wrong in the middle where it evenly partitions. But as soon as you get some skew, this will be very close to this, whereas this will be still pretty far from this. You have to get pretty close to the edge before you're not losing much here, whereas pretty quickly you're not losing much here. That's the intuition. Try it, see what happens with xn, and it won't work. See you Wednesday.